Welcome back. In the previous video, we were talking about isotopes and what an isotope was. This is new information. What I'm going to tell you is that some isotopes are stable, and an example of a stable isotope is carbon-12. So this particular kind of carbon atom is stable. What I mean by stable is if you have a carbon atom sitting next to you, you come back a billion zillion years from now, unless something crazy happened, it's still probably going to be a carbon-12 atom. Nothing's really going to change about it. Now, I don't expect you to be able to look at this symbol or this picture and say, oh, that's going to be a stable isotope. I'm just telling you that that's the way it is for carbon-12. Some isotopes are unstable. This is carbon-14, and again, I don't expect you to know this, but I'm just telling you that carbon-14 is unstable. What I mean by unstable is if you wait around long enough, carbon-14 is going to turn into something else. So because carbon-14 turns into something else, we can write an equation for what it turns into. And I'm also going to have the most amazing animation ever that you've seen to show you what happens to carbon-12. So focus in around there, and I will show you. If you wait around long enough, this will happen to carbon-14. So let's watch that again. What is this gray blob there? Well, it's a neutron, and what happens to it? Well, it turns into a proton. So that neutron turns into a proton, and that is also an electron. And what I'm going to tell you is the electron is not happy being in the center of the atom like that, so it's going to get fired off into the distance. And check this out. Wasn't that amazing? That was pretty amazing. Let's watch it again. In fact, let's watch it from the beginning. We have carbon-14 here. It has this neutron. That neutron turns into a proton and an electron. The electron is not happy being there, gets fired off. So the question is this carbon anymore? Is this a carbon atom? And you can pause and think about that. If you unpause the video, the answer is no, it's not carbon, because carbon has 6 protons, and this doesn't have 6 protons anymore, it has 7. So you can look up in the periodic table what kind of atom has 7 protons. You can do that if you want, but what you'll see is the atom that has 7 protons is nitrogen, and the symbol for nitrogen is a capital N. So carbon-14 turns into nitrogen. Not only does it turn into nitrogen, but it turns into a nitrogen that has a mass number of 14. So what we can do is we can say, well, carbon-14 turns into nitrogen-14 like that. And remember, it also fired off an electron. So the other thing that we're going to write on the right side of this equation is we're going to write a lowercase e for electron. We're going to put a number in the upper left because we want to tell people how much the electron weighs. But if you remember from back in the beginning of the course, the electron doesn't weigh enough to count. So we're going to put a 0 there. And then in the lower left, where I said the lower left number means the number of positive charges, well, the electron doesn't have a positive charge. It has a negative charge. So what you write when you write the symbol for an electron is you write a -1, because the electron has -1 positive charges. You can think of it that way. So this is our equation. Carbon-14 is unstable. It turns into nitrogen-14, and it fires off an electron into the distance. Now, a couple of things. This is called a decay equation, because when you have an unstable isotope and it turns into a new isotope, you say that your unstable isotope decayed. So I want you to know that term. This particular kind of decay is called beta decay. And this little puffed up B looking thing here is the Greek letter beta. There's a reason why it's called beta decay. It's not particularly interesting, but I'm going to tell you. And that is, if you know the letters of the Greek alphabet, there is a Greek letter called alpha. That's the first letter, and it's written kind of like a weird lowercase a. The second letter of the Greek alphabet is beta, and it's written like a weird little b. Third letter of the Greek alphabet is called gamma. It's drawn like a little ribbon, like an upside down ribbon. And because scientists are pretentious, they have a tendency to name things after foreign alphabets, and there are many kinds of decay that you're going to see. Beta decay, the kind that you're seeing here, is the one that they found second. So they found a different kind of decay before this one, and they called it alpha. Guess what the third kind of decay was called? I'll give you a hint. There you go. All right. So this particular type of decay is called beta decay. Now, I don't really care that you know what beta decay is, or alpha decay, or gamma decay, but the names are going to come up because you can put them into categories, but you're not going to be tested on that. Okay, a couple other things. If I did not show you this diagram over here, this fancy animation where the electron goes flying off into the distance and whatever, but I showed you an equation like this, where I said, look, carbon-14 spits out an electron and it turns into something new, but I hid what the new thing was from you. And I said, I don't know what that is. Could you please figure that out for me? There's an easy way to do it without looking at a diagram like this. And the easy way to do it is this. You split the equation down the arrow, and you look at everything on the left side. Now, there's only one thing on the left side, so this is pretty easy. And you add up the weight of everything on the left side. Well, here's the weight of everything on the left. It weighs about 14 AMU. The weight of everything on the right side has to add up to 14 AMU as well. So you look over here and you say, well, the electron has a weight of 0. There's our 0. What that means is whatever the question mark is has to have a mass number of 14, because the weight of everything on the left side of the arrow has to match the weight of everything on the right side of the arrow. We're not quite done because it's still a question mark. The last thing you do is you add up all the positive charges of everything on the left side. Well, carbon has 6 positive charges. There's our 6. So if we add up all the positive charges on the right side, it also has to add up to 6. But this electron has a -1, so we have to say what number is going to go here plus -1. What number plus -1 is going to add up to 6? Well, the number that has to go there is a 7, because 7 plus -1 equals 6. And now you know the top number of the question mark, you know the top left number of the question mark, you know the bottom left number of the question mark, and the bottom left number is enough to tell you what you are. You look up who has 6 positive charges in the periodic table, and you'll see that it's nitrogen. And so you put a capital N here. And so this is the type of thing that I'm going to expect you to be able to do on a quiz or a test. In other words, you won't see a pretty picture like this. You'll see a decay equation with one missing piece. And you play this game where you say, well, how much does everything weigh on the left side of the arrow? 14. Everything on the right side has to add up to a weight of 14, so I'm going to put a 14 next to the question mark. How many positive charges are on the left side of the arrow? 6. All right, the number of positive charges on the right side of the arrow has to add up to 6. So this must be a 7. 7, the only thing that has a 7 is nitrogen, and then we're done. So that type of question is going to show up on quizzes and exams. And just in case it wasn't clear, beta decay is when you have an unstable isotope and you fire off an electron. There are other kinds of beta decays they don't have to just do with carbon-14, and you're going to see one on the next slide. Here is another sort of sample problem with a question mark. You can pause the video, but this is just another example of beta decay because you can see an electron is getting fired off. This part of the periodic table is enough to let you figure out the identity of the question mark. So like I said, you can pause the video and think about that. Unpausing the video, well, we're going to split the equation down the arrow. We add up the weight of everything on the left. Now again, there's only one thing on the left side, and the weight is 60. So everything on the right side has to add up to a weight of 60. The electron doesn't weigh anything, so our question mark has to have a mass number or a weight of 60. Then we look up how many positive charges CO has. CO is cobalt. Cobalt has 27 positive charges. So everything on the left side adds up to 27 positive charges. We have to add up to 27 positive charges on the right side. So you say what number plus -1 is going to equal 27? And the answer is going to be 28. Then we can say, well, who's got 28 positive charges? Well, here it is. It's nickel. So if we wanted to write the complete equation, we could write it like this. We could say cobalt 60 decays into nickel 60, undergoing beta decay, if you want to sound really fancy. Now, to me, this is kind of like balancing an equation, but to me it's also easier because all you're doing is adding up top numbers on the left, making sure that the top numbers on the right add up to the same number, adding up bottom numbers on the left, making sure that the bottom numbers on the right also add up to the same number. But that's just another example of beta decay. That's the end of this video. In the next video, we're going to do a different kind of decay.